Kiddo. So welcome everybody. Good afternoon or good morning or good evening, depending on where you are. This is our 164th Reading Online Sports Economics Seminar. Really great to have lots of people here, despite, as we've been talking about, all the sporting distractions, European Championships match at the moment. The main development, if you want to call it that, since we last met, is that because we always, every time, have some people who can access the chat and some people that can't, what I've done in the last few weeks is establish a WhatsApp group so that hopefully everyone can access that if they want to, and then people can share comments that they might have that they want to attract my attention or we want to do other things. So if you do want to be in that WhatsApp group and you're not already, then please do get in touch with me, drop me an email with your number and I can add you to that group. Hopefully it also makes us that bit more sociable as well. Dennis isn't here. Dennis's wife always complains that we sports economists are not very social and we don't have each other's phone numbers and we can't get in touch with each other. So this is a way to address that. Please do let me know if you would like to join the WhatsApp group. We have Daniil Starikov presenting today. His talk will be on do the riders compete strategically or just drive as fast as possible? Daniil, please do take away your talk.
Thank you. Okay. Today I will present our joint project with Dmitry Dagaev and Gleb Vasilyev. Do the racers compete strategically or just drive as fast as possible? In the beginning, I think that it is necessary to introduce the main rules of Formula One that are essential for understanding of what we do in our analysis. So I will start with it. And Formula One is the highest class of international racing for open wheel cars. Usually 20 drivers compete in each season with each other, and they participate in 20 or 24 race weekends. It depends on how many race weekends are in the season. And for each weekend, the driver gets some points that are taken into account then and used for calculation of the final standings to determine who is the champion. Each race weekend consists of 3 parts. First, it is 3 free practice sessions in which the drivers just prepare for the main parts of the weekend. They just test some new details and get accustomed to some specifics of the circuit on which they are racing. The second part is qualifying session that is held on Saturday. It determines the starting order of the drivers in the main race. So they just need to drive as fast as possible in this session to demonstrate the best possible time and to start as high as they could. And the main part is race on Sunday. And the points are awarded for this race for the top 10 fastest drivers, for the drivers who end up in the top 10 drivers in the race. And if the race is held in dry conditions, then each driver is obliged to do at least one pit stop, in which his team's pit crew changes all the tires on his car. And there are 3 different compounds of tires for dry conditions: soft, medium, and hard, and they differ in a few dimensions. First, they differ in the wear of the tires. So it is easier to overcome the longer distance using hard compounds than soft or medium. And the second difference is the pace that these compounds allow to achieve. The drivers can drive faster if they use soft relative to the medium or hard, for example. And as I said, if there is no rain in the race, then all drivers are obliged to use at least 2 different compounds. They, of course, may use more if they want. If there is large degradation, then can go for a 2-stopper race, and they can use, for example, soft, medium, soft, or soft, hard, medium, and any combinations of these 3 compounds. but it is not often the case, and we focus here only on one-stop races. And it is also should be noted that if the situation on the track is hazardous, so if, for example, one of the drivers crashed his car in the barrier, then there might be yellow flags at the circuit, and all drivers must slow down, and therefore pitting at this moment can be very good in terms that it will allow to save some time relative to other drivers. And the pit stop strategies are essential for the success in the races, and we want to introduce one motivating example that may show why we believe that it was worth studying the optimality of different pit stop decisions. So probably many of you have heard of the Monaco Grand Prix. It is one of the most famous Grand Prix in the calendar of Formula One. And it is essential not to lose any positions during the pit stop there, because overtaking in the circuit is extremely difficult. And in 2022 Monaco Grand Prix, there was a situation that two Ferrari drivers, Charles Leclerc and Carlos Sainz, they were first and second by lap 14. But then two Red Bull drivers, who were Sergio Perez and Max Verstappen, were third and fourth, right behind the leaders, and the conditions on the track were wet, so all the drivers were on the wet tires. And on lap 17, Sergio Perez decided to pit for intermediates, and then he was followed up by Max Verstappen and Charles Leclerc on lap 19. But Ferrari decided to leave Sainz on track on wet tires until lap 21. And then on this lap, both Ferraris, and Sainz and Leclerc, pitted for slick compounds because they decided that there will be no more rain, and Sainz decided to skip one stop, and Ferrari decided to instruct both of the drivers to stop simultaneously on one lap. And it was a very bad decision because as Ferrari drivers were very close to each other, the pit crew didn't manage to serve Leclerc properly, and he became fourth instead of winning his home race. And he was very sad about this, and a lot of discussion in the news and among the fans of Formula One was about this strange strategy of by Ferrari. And moreover, Sainz remained second, but Perez, who is the driver of Red Bull, overtook both Ferrari drivers and won this race exactly because he had the better strategies than two Ferrari drivers. So we believe that this example shows why pit stop strategies are essential for the success in the races. And now we would like to discuss some literature review that to focus on some research that studies the pit stop decisions. First, we would like to know that many researchers focused on optimization of pit stop strategies using neural network and dynamic programming. But these papers do not pay much attention to the drivers' interactions and do not want to study whether they play a significant role in decision-making process of the drivers. But we want to do this. And one of the papers that we know that focus on something similar is the one about NASCAR, but it focuses on the very specific pit stops, specifically the pit stops during the yellow flags at the end of the race in NASCAR. But we want to focus on all the interaction during green flags during the normal racing conditions. And to the best of our knowledge, there are no papers that do exactly this. So speaking of the pit stop strategies, Hellmeyer showed that in the absence of the driver's interactions, the problem of choosing the optimal lap for a pit stop is just a quadratic problem. So the maximization problem can be solved. And if we assume that all drivers have the same tire degradation and car characteristics, then they would like to pit on the same lap just to minimize the time in the race. But actually, it is not always the case. the drivers might want not to minimize the time, but minimize their position. In some situations, they may decide to choose an alternative lap that will not lead them to the lowest possible time spent on the race, but it may allow them to overtake the opponent and keep him behind after that. And one of the strategies that can allow to do this is an undercut strategy. If the driver follows his opponent but cannot overtake him, he may want to stop earlier than he planned, and then this strategy is called undercut. The pros of this strategy are the following. The driver, who is the person who is behind another opponent, gets fresh tires earlier than his opponent, and therefore he has a tire advantage for a period until the leader stops. And this tire advantage may be very strong, and it may allow to overtake the driver. But of course, there are some cons. For example, this strategy makes the second stint longer, and the driver who stops earlier will need to spend more time on the second compound, so it will be older than the compound of his opponent, and the former leader might try to overtake the person back and to get his position back if he have enough tire advantage in the second part of the race after the both drivers stop. And the alternative strategy is overcut. It is the situation when the driver who is behind wants to stop later than he planned and later than his opponent. Then he will not get fresh tires until he stops, so he will lose some time while he will be on the older tires. But then in the final stint of the race, he will have fresher tires than his opponent, and it may allow him to overtake his main rival. And furthermore, something may happen on track, and something may cause yellow flags, and it will allow the driver to make a cheaper pit stop. He will save some time relative to other drivers, and this is one of the reasons why the drivers may want to do overcuts. So the summary is the following. Undercuts, in other words, stopping earlier than the driver in front, may be effective because of the tire advantage during the time between the stops of the drivers, and overcuts, stopping later than the driver in front, may be effective because of the tire advantage during the time between the latest stop and the end of the race. And the research questions that we pose in our study are the following. Are overcuts and undercuts effective in the sense that they allow the drivers to overtake the opponent? How should the drivers behave if they are rational and aware of the effectiveness of different strategies? And are actually Formula One drivers rational, and do they follow theoretical predictions or not? This is what we are focusing on. So now I will introduce the theoretical framework that we developed in our paper. We assume that there are two drivers, purser and leader. They participate in a race consisting of n laps. The goal of each agent is to maximize the probability of finishing in front of his opponent, and we assume that the drivers are close enough to each other, but the purser he's behind, but he cannot easily overtake the leader, so he wants to try some alternative pit stop strategies in order to overtake his rival. And after each lap, they sequentially make their decisions to stop or not to stop. And the leader, as it is expected, makes his decision first, and then the purser observes his choice and makes his own. He may stop if he sees that the leader stops, or he may not stop if he doesn't want. But it is important to note that the leader learns about the purser's decisions after he makes his own decision on this lap, so he can react on the purser's action earlier than on the next lap. So If, for example, on lap 30, the person decided to stop, but leader decided not to stop, he cannot change his mind and decide to stop. But the person has the opportunity to, for example, act opposite to his opponent. He can observe what the leader does, and then he can stop or not stop, depending on what he wants and what the leader does. And after one driver stops, another driver learns about it, and he just chooses the lap when he will stop. And when both decisions are made, payoffs, which are the probabilities of finishing in front of the opponent, are realized. So now let's talk about these payoffs, about the probabilities. First, let LL and LP be the laps when the leader and purser stop respectively. These choices split the timeline of the race into three parts. First, as we noted as 0, the time before the first stop, then period between the stops, and finally a period between the last stop and the end of the race. We assume that by the end of period 0, so exactly before the first stop of the drivers in a pair, the purser is still behind the leader. But then the situation may change, and it is uncertain what will happen. So we model the probabilities that the purser will overtake the leader by the end of two periods, by the end of their stops and by the end of the race. And speaking of the first probability, the probability of overtaking the leader by the end of period 1, which is right after the stops of both drivers, we let these probabilities be noted in the following way. For example, P1U is the probability that using the undercut strategy, the purser is in front of the leader by the end of period 1, which is the period, which is the lap right after the stops of the drivers. And the similar probability is introduced for the cases of overcuts when the leader, when the purser decides to stop later than his opponent. If the drivers stop on the same lap, then the probability of the take is very small, but we assume that it is positive, and we will further discuss how we estimate it. Yeah, and then when the stops are done, there's still some time in the race until the end. And even if the driver is in front of another driver, he needs to keep this position, and it may be either easy or difficult depending on the tire advantage and who has this tire advantage. So speaking of the cases, when there was an overtake right after the stops, we denote it as O equal to 1, O from overtakes. Then the probabilities of standing in front of the former leader by the end of the race are denoted in the following way for undercuts and overcuts respectively. And the similar observations or similar probabilities are introduced for the cases when there was no initial overtake right after the stops. And this allows us to then compare the total probability of purser's success in case when he undercuts or overcuts the leader. And the formulas are here in the bottom of this slide. And now we need to discuss what we expect from these probabilities. Based on our arguments about tire advantage, we expect the following. First, the probability of being of overtaking right after the stops using undercut should increase with the tire advantage of the purser and the number of laps between the stops. The intuition for this is the following. When the purser stops earlier than the leader, then he has tire advantage. He has fresher tires and he may drive faster than his opponent. And this is the reason why we expect that the tire advantage should positively affect this probability. And the number of laps between the stops, it is just the length of the period for which this purser has tire advantage. And again, it is intuitive that the number of laps should increase this probability. Then, if undercut was successful and the purser is in front of the leader right after the stops, we expect that this probability will be high, but it should decrease with the tire advantage of the leader and the number of laps between the stop of the leader and the end of the race. The intuition is very similar, but now the tire advantage plays for the leader, and he should benefit from it. So the probability that the purser will keep the position, will still be in front of the leader, is increasing with the tire advantage and the number of the laps. And when the cut was unsuccessful, when it didn't allow to overtake the leader right after the stops, we think that the probability that an overtake will happen is very low, because during the remaining laps, the leader has advantage, and if the purser didn't manage to overtake his opponent before the stop and during the time between the stops, then it is very unlikely that, having worse conditions, he will overtake his rival. And the probabilities, we also discuss the probabilities of overtakes. First, we think that it is unlikely that the drivers will often overtake the leader right after the stops using overcuts, because the leader has tire advantage and he is faster than the purser, and we do not expect that they will often be in front of the leaders right after the stops. But if they, for some reason, managed to do this, then they are likely to keep the position because they have the tire advantage, and they are very likely to stay in front of the former leader. And if they didn't manage to overtake, then they still have the opportunity to do this because they have tire advantage, and we expect that this tire advantage and the number of remaining laps will increase the probability of finishing in front of the leader by the end of the race, even in the cases when after the stops the purser was behind the leader. So let's now discuss the data and the methodology that we use for the estimation of these dependencies. We use the fast-of-1 package in Python to collect the information on all races from 2018 to 2023 season. And overall, we have 120 races. For each driver, we have the data on his tires, the data on the distance to his closest rivals in front and behind, and the data on track status during each completed lap. And of course, we have the data whether the driver stopped or not. And we restrict our sample to the cases when at least one driver stopped. And for these cases, we look at the driver who stops and his rivals in front and behind. So when we focus on the stopping driver and his opponent in front, then we attribute it to potential undercuts, because the driver who is behind his opponent is pitting earlier than his opponent, and therefore it is an undercut according to our definition. And the pair of the drivers, when the leader is stopping but the purser stays on track, we assume that it can be a potential overcut, because again, it is just the definition of overcuts, the situation when the driver who is behind stops later than his rival in front. And finally, we exclude some pit stops if, for example, it was raining in the race, because we are focusing only on the races held in dry conditions. Second, we delete the observations if one of the considered drivers didn't finish for some reason, for some technical issues, or if he crashed into the barrier. We also focus only on the drivers who were sufficiently close, and we choose the threshold level to be 150 meters on average at the lap before the first stop. So the drivers should be close enough to each other so that they are considered to be affecting their decisions and fighting, competing strategically. And we also delete the observations for which at least one driver benefited from the presence of yellow flags. And we delete the observations for the first or last 5% of the race. First percent of the race, because the stops during this time period usually happen. They usually happen because of some technical issues with the car, and we don't want to focus on it. And the last 5% of the race, the stops during this period usually happen because the driver is not competing with anyone on track, and he just wants to set the fastest time in the race to get one additional point into the standings. And we also do not focus on the pace of drivers that made different number of stops, because we assume that they are on very different strategies, and we are focusing on those who choose quite similar strategies, but just someone pits earlier or later than another one. And here are the summary statistics that we have. We split the data set by overcuts and undercuts, and the first observation that can be made that the number of observations for overcuts is much larger than for undercuts, and we will later discuss this. And speaking of the variables that we have, of course, the pit lap of the purser, of the leader, the number of laps. We have the delta of laps and delta of tires between the stops and between the latest stop and the end. These are the variables that are used for estimations of the probabilities that I introduced a little bit earlier. And it should be noted that different races have different number of laps. So we decided to divide the lap difference by the number of laps. So we interpret these variables as the share of the race that passed between the stops and that is remaining after the latest stop and before the end of the race. And we also have the dummy for overtaking right after the stops and overtaking by the end of the race. These are the probabilities that we are estimating, and let's focus on it a little bit more. Here we can see that the probability of overtaking right after the stops is much higher for undercuts than for overcuts. And we believe that it happens because of the tire advantage that the drivers have when they pit earlier than their opponent. But then they not always can keep their opponent behind, and they lose position quite often, and the probability of finishing in front of the leader for overcuts and undercuts overall are very similar. And we also have the data on average distance between the drivers that we use to restrict the sample to only the drivers who are close enough to each other. And we also have the data on team strength and the relative difference between the strength for the considered drivers, and the data on the compounds of tires that these drivers use in the race, before and after the stop. And yeah, let's focus here again on the productivity of overcuts and undercuts. This graph demonstrates what I was talking about 1 minute earlier. We can see that right after the stop, right after both of the drivers stop, the probability that the former cursor is in front of the former leader is higher in cases of undercuts because of the tire advantage, as we believe. And furthermore, the cursors are in front of the leaders in more than 50% of the cases, which is very large and probably undercuts are very, very effective, and the leaders should know about this, and probably they should think of protecting themselves from these undercuts. And here is the table for the final overtakes, whether the cursor is in front of the leader by the end of the race. We split the observations based on whether there was or not the overtake right after the stops. And we can see that if there was an overtake, then it is very likely that the driver will keep his opponent behind, and he will win this race between these two drivers in more than 50% cases. But if there was no overtake, then speaking of the undercuts, it is very unlikely that it will happen after the both drivers stop, because the tire advantage is because the leader has the tire advantage and he's in front, and he's unlikely to let the person pass him. But in case of overcuts, the number of cases when the person managed to overtake the leader is a little bit higher, and probably the tire advantage during the period between the latest stop and the end of the race is also effective for the purses that can be seen from this figure. And now let's discuss the methodology that we use. In the left-hand side, we have a dummy for overtaking by the end of the considered period. It is either the moment right after two drivers stop or the moment of the end of the race. Yeah. And in the right-hand side, we have delta of the laps that passed between the stops or that is remaining after the latest stop, depending on what probability we are estimating. And we have the estimation of tire advantage, which is the difference in ages of the tires, which are measured as the share of the race that was completed using these tires. And we also introduce in some of the specifications the squared terms of delta laps and delta tire and the interaction term. And we also include some set of control variables. These are the variables about the tire compounds of the driver and of the leader and the person before and after the stops. And it is the strength of the relative strength of the teams of the drivers. And finally, we include the circuit and season-specific fixed effects to control for some unobserved time and circuit invariant characteristics. And let's go to the results of the estimations. First, let's focus on the probability of successful undercuts in terms of the probability of overtaking the leader right after the stops for undercuts. And we expected that it will be increasing with the tire advantage and with the number of laps passed between the two stops. And we can see that in the fourth column, which is the most preferred one because it includes the squared terms, interactions, and control variables, we can see that actually it is the case. Both the laps and tire advantage have positive impact on overtakes, and the dependence is quadratic, so it is inverted U-shaped dependence. But based on these estimates, the probability keep increasing for all of the observations that we have. I mean that the share, I mean that the top of this parabola of this U-shaped dependence is not achieved in our data. So we believe that the effect of laps and tires is increasing, but the effect of each additional lap is just lower than from the previous one, and this is what we expected to find out. Now let's focus on the probability of finishing in front of the leader when the undercut allowed to overtake the leader right behind the stops of the drivers. We expect that it will decrease with the number of laps remaining and with the tire advantage. We can see that it is usually the case, but it is not always significant. And one of the reasons for this is that we have quite a few observations for the estimations and quite many variables that we include in the specifications. But all in all, the probability that the person keeps the former leader behind decreases with the leader's tire advantage and the number of remaining laps. And now, speaking of the probability of overtaking by the end of the race for undercuts when the leader kept his position right after the stops, we expected that it will be very low. And we can see from the row with the mean of dependent variable that is actually very low. It is about 5%, and we have seen it from the graphs that I included in the section with the data and methodology. And in one of the specifications, the probability increases with the number of remaining laps. It also could be the case because when there are more laps remaining, then something may happen to the driver in front. For example, he may make a mistake, and even if you don't have the tire advantage, then you may be in front if, as I said, something happened to the driver in front. But we don't pay much attention to these significant coefficients because in the other specifications, it is not really significant. And now let's go to overcuts. Overcuts, as I said, are the situations when the person stops later than the driver ahead, and we expected that the drivers will quite rarely be in front of the leaders right after both of them stop. But we can see that sometimes the drivers who make overcuts manage to overtake the leaders, and it increases with the number of laps in the specifications in which we do not control for the laps squared and the interaction. So probably, again, consistent with the explanation for the previous table, when there are many laps remaining, something may happen, and the person can overtake the leader even if he doesn't have the tire advantage during this period. Now, here is the probability of overtaking by the end of the race for overcuts when the leader lost his position after the stops. Then then the person is now in front, and he has the tire advantage, and we thought that he will unlikely lose the position. But in some of the specifications, we can see that he may lose it. For example, if there are too many laps remaining, again, now something may happen to the person who became a new leader. Something may happen to him, and he will lose the position back, and he will finish behind his main rival. And the final, I think, one of the final probability for overcuts the probability of overtaking by the end of the race when the leader kept his position right after the stops. We expected that this probability will be increasing with the number of remaining laps and the tire advantage, which is the benefit for the purser. And actually, we can see that it is the case. The dependence is positive for the laps and for the tire advantage, and this is what we expected. Yeah, and finally, we looked at the cases when the drivers stopped during the same lap. We can see that it is quite a rare situation, and the drivers who are close to each other don't really want to stop at one lap. They want to try some alternative strategies like undercuts or overcuts, trying to overtake the opponent. And we can see that the coefficients are insignificant, but the probability slightly increases with the number of remaining laps, which is consistent with the previous explanation that something may happen and the driver may overtake the leader, even if there is no tire advantage. And now, after we estimated all the probabilities, let's put them back into the theoretical framework and look what we get. From the previous estimations, we used the specifications that include quadratic and interaction terms and control variables because this specification is the most precise. And using these estimates, we calculate the probabilities of overtaking for all possible drivers' decisions. And further, we solve the finite repeated game by backward induction and find the equilibrium. Yeah, and it also should be noted that in the regressions, we used the linear probability model. So it is possible that the probability will be higher than 1 or lower than 0 for some observations. So we just take the minimum between the 1 and the actual probability and the maximum between 0 and the actual probability to get rid of these strange observations here. And here are the results of estimation of these probabilities for different actions of the purser and the leader. Here we assumed a race that consists of 100 laps, just to have a nice graph. And the color in this figure on the left-hand side of the slide shows the probability of overtake by the end of the race for given choices of drivers. So red corresponds to a high probability of overtake. The purser is in front of the leader by the end of the race, and yellow signals a low probability. And what can we see? For example, we can conclude that pit stops in the beginning of the race cannot be optimal. Let's look at the cases when the leader stops in the very beginning of the race. This corresponds to the cells in this heat map in the bottom of the figure, for example, in the first 10 laps. Then the purser may choose the optimal lap such that he will be in front of the leader by the end of the race with 100% probability. The dark red area signals about this. We can see that if the leader stops in the very beginning of the race, then the purser decides to stop in the very end of the race, because after this stop, the tire advantage of the leader is very low, but in the end of the race, it is very high, and the purser has the tire advantage, and he can easily overtake his opponent in the end when he stops and gets much fresher tires. And the opposite situation can be seen for the cases when the purser stops in the first 10% of the laps. The white cells in this corner signals about this. When the purser stops in the beginning of the race, the leader decides to wait for the end of the race and stop there, and win the race between these two drivers with 100% probability. And another very important conclusion that we made from this graph is that undercuts become very effective closer to the end of the race, while overcuts become less effective. And we can see this in this corner. We can see that in the cases when the person stops a little bit earlier than the leader, the area is very red. So the probability that he will overtake the leader is very high. But the area that is below the main diagonal of this matrix is very yellow, light yellow, and it signals about the fact that if the person stops a little bit later than the leader, then he's very unlikely to win the race if the pit stops happen in the end of the race. Yeah, and these are the main conclusions that we make from this graph. Now let's focus on some specific decisions of pursuers and leaders in the race. Here I plot the probability of overtaking for different choices of the pursuer and for given leader's action. We assume here that the leader stops at the lap of 25, and for example, pursuer knows this perfectly, and we want to look at what strategy is optimal for him. And again, consistent with the figure that we discussed just in the previous slide, the pursuer wants to make overcuts and to stop in the very end of the race in this case. And the probability of the overtake will be very high, much more than 50%. And now let's focus on the case when when the leader stops in the middle of the race, on the lap 50 out of 100. And we can see that here undercuts are very effective. They allow to overtake the leader with the probability of about 43%. So if the person stops one lap earlier, then he is very likely to overtake the leader. But if he stops one or more laps later, then he will overtake the leader with the low probability. So in this case, overtakes are less effective than undercuts, and it was also shown in one of the previous graphs with the heat map for the probabilities. And the final case when the leader stops in the end of the race on lap 75, we can see that undercut is very, very effective. It is even more effective than it was when the driver stopped in the middle of the race. And overcuts are even less effective. And this figure shows it better when I plot all of these three cases. So yeah, we can see that when the drivers wait for the end of the race, or when the drivers stop in the very beginning of the race, then the probability of overtake is very large. It is very likely that the pursuer will effectively respond to bad actions of the leader. But if the leader acts quite optimally and stops somewhere in the middle of the race, then it is more difficult for the pursuer to overtake him using the strategy. But anyway, there are still some good and bad strategies, and they should know about this. And now let's go to the solution of the model. I think it is necessary to remember the game that we have. Having the probabilities for overtakes for all driver sections, we can find the equilibrium. We previously described the game, and it was finite. There were n laps, and the drivers consecutively chose whether they stop or not. And after both decisions were made, the payoffs were realized, and the payoffs were the probabilities of finishing in front of the leader. And as the game is finite and it is obvious how the drivers make their decisions and in which order they make the decisions, we can solve the game using the backward induction, and we provide the results in the following slide. Here are the main results of our simulations. We run the simulations for different realistic values of numbers of laps and find optimal decisions by the leader and the purser. We choose the number of laps from 40 to 80 because the minimum number of laps in the Formula One calendar is 44 in Belgium, and the maximum number is 78, as far as I remember, in Monaco Grand Prix. And here we can see the optimal decisions by the leaders marked in red, and the optimal decisions of purser are marked in blue. We can see that in all the cases on which we focused here, the equilibrium is that the purser will stop somewhere after the middle of the race, and the leader will stop somewhere after the middle of the race, and the purser will try to overcut the leader. So this is the equilibrium suggested by our model. But we have seen that undercuts were very effective, and in fact, we have that the equilibrium is the pursers who are doing overcuts. And why do this happen? Moreover, in the data, we also have that there are many overcuts, and there were very few undercuts, but they were very effective in the graphs. And we think that the explanation for this is the following. The leaders are aware of the undercut's effectiveness, and they want to try and protect themselves by pitting earlier and not allowing their opponent to undercut them. And therefore, this just makes the pursers pit later than the leaders, and they cannot do undercut, and they have to do overcut, trying to overtake the opponent. And we try to test this hypothesis. We check this by comparing the stops happened when the drivers were close to each other to the pit stops when the drivers were quite far from each other. The intuition is the following. When the driver is very far from any opponent, then he is not responding on their actions quite much. He just tries to drive as fast as possible and to minimize his time of the race, as it was shown by Hellmeyer and co-authors in the paper. And we assume that the drivers who are far from other opponents actually do this. But when the drivers are close, they start thinking of what other drivers may want to do, and they want probably to protect themselves from undercuts, and they may want to stop earlier than they would do if they were far from their rivals. And this table suggests that it actually can be the case. First, let's focus on the second column. Drivers who undercut their opponents stop earlier than other drivers, and it is just the key idea of undercuts. The driver wants to stop earlier and to get fresher tires and to overtake the leader using this. Yeah, and this is the sign that we expected to see. But speaking of the overcuts, again, we can see that the leader stops earlier than he would stop if he was not fighting for the position with some very close rivals. So we think that it can be explained by the idea that the opponent, that the leader is aware of the effectiveness of undercuts, and therefore he wants to stop earlier so that the purser cannot undercut him, so make him doing overcuts. And this is the main finding that supports our hypothesis. And summing it all up, we developed a theoretical framework that allows us to study the driver's interactions in the races with pit stops. Further, we estimated the probabilities of overtakes for different strategies using the real-world data on Formula One races. And then we calibrated the model, and it suggests that the best strategy for the drivers is to stop earlier than the opponents in front, so to make undercuts. But in the equilibrium, the leaders are aware of this and protect themselves from undercuts and make the leaders do overcuts. And the table from the previous slide is the empirical evidence that make us believe in this hypothesis, that the leaders react to potential undercuts and pit earlier than they would do if there was no driver behind them. So coming back to the name of our paper, we conclude that the drivers do actually compete with each other using different strategies, and they respond to the strategies of the other drivers. So they are rational, they understand which strategies are effective, and they try to respond on them properly. And yeah, that's it. Thank you for your attention. I will be very glad to answer the questions and to listen to the comments. Thank you.
Great. Thank you very much, Daniil. I'm going to give you a Teams round of applause. That was a really interesting talk, very thorough piece of work on a very complex decision-making process for teams. We've got lots of time for questions and comments. So if anyone has any questions or comments, please do raise your hand. Georgi.
Yes, hi, Daniil, thank you so much for sharing the findings. Indeed, like James mentioned, a very thorough work. My question is pertaining sort of the additional evidence. Have you found any degree of deviation between the drivers that perhaps are in the same team in terms of the overtakes, as well as that may have been on the same team years ago? For instance, Fernando Alonso has been there in Formula One for years and might have made a few friends, might have made a few enemies. So have you explored that at all, and what do you have to share on that front?
Okay, so you're asking about whether some experienced drivers act differently and whether
no. It's a two-part question. So one is, okay, if I'm on the same team, if both of my drivers are driving for Ferrari and one overtakes the other, do those situations happen less frequently? And another one is, do drivers that perhaps have been driving for the same team in the past, is there a difference in their behavior in terms of overtakes?
Okay, thank you for your question. I think I understood it. Speaking of the teammates, I think that the overtakes happen very rarely, and if they happen, they're usually the team orders, when the team says, just please let him go, he is faster than you, and don't destroy our race. So no, we didn't focus on this. We may look at it and check whether there are enough observations when some teammates competed with each other. But my guess is that there will be very few such observations. And speaking of the former teammates, it is a very interesting idea. I hadn't thought about this. I will point it out and probably look at this in the further research. Thank you.
Great, thanks, Georgi. Julio.
I'm not an expert in F1, but my wife, she is. So she was screaming during the presentation, and my kid also was screaming during the presentation. So maybe I missed some points. So I think that you try to analyze whether the overcuts and undercuts are useful at the end of the race or during the race. I mean, you analyze the final position, or whether an overcut or an undercut is useful, since the.
Okay. Okay, we focused on both cases. We focused on the probability of overtaking the opponent right after the stops, so the intermediate position, and then we focused on the final position. Yeah.
Okay. Okay. And
the final results were for the final position because it was, of course, more important for the standings.
Okay. So two things. In the simulations, you have the laps. I think would be more useful to get not the laps, but the percentage of the race. You know that in some
it is
circuits,
the
difference
I actually use the share of race. We actually use the share of race. I just
okay. Okay.
But, yeah.
So it was a mistake in the okay. And my final comment is about the R-square of some models. I was really amazed since I guess you estimate a probability model, a linear probability model, and you get at some points 0.7 R-squared, which is something really big, and even more considering that some very few variables were significant. So it was quite complicated. I remember I was amazed by some results because the R-square was really high for this kind of model. And I think it could be quite difficult to understand why it's so. In this kind of model, an R-square more than 0.5 is quite difficult to get because the data. And my very last comment, if you have a report or a working paper or something similar, I will be really nice to discuss with my wife.
Okay.
Okay,
thank you.
Great. Thanks for that, Julio. And then next is Clay.
Hey, yeah, I really like this paper. I love to see F1 studies. I think we need to study more of that. I have one kind of comment and something you might want to think about. You're framing this kind of like as drivers' decisions to pit, but I think in the practice of F1, the decision to pit is often done by teams. So it's sort of a team ordering a driver to box, not necessarily a driver choosing that. It doesn't change anything you've got, but you may want to think about like framing that.
Yeah.
And second is, you're treating tire degradation as a constant throughout this. But I think if you get somebody in the racing community, a driver or a team or something, they may like push against this because, some drivers may be better at saving tires than others. And one reason maybe why you're seeing undercuts more effective than overcuts is because if you're trailing, you have to push more to make up the difference, which could lead to more tire degradation.
Yeah, so thank you very much for this comment.
That may be something to think about.
Yeah, we'll think about this. Thank you.
Great, thank you, Clay. Any more questions and comments? One fairly ignorant question I had was that I presume, obviously, when you talk about the decision to take a pit stop at any particular point, presumably teams and drivers aren't totally flexible to choose at any point because they only start the race with a certain amount of fuel on board and they start with a certain set of tires for the conditions. I mean, to what extent are the drivers and the teams flexible in the choices that they make? Is there a lot of flexibility or are they quite constrained?
Okay. Okay, here we calculated all the probabilities. Yeah. Actually, I think in terms of fuel, it is definitely possible to stop at any moment because the refueling is prohibited in Formula One for many years. I don't remember when it was prohibited. So yeah, fuel is not a problem.
Okay.
Speaking of the tires, it depends on the track. For some tracks, there is very low degradation. For example, in Monaco Grand Prix, it is possible to overcome the whole distance using only one set of tires. But nobody does this because it is prohibited by the rules, because the drivers need to choose at least 2 different compounds, but it is possible. On some other tracks, it is more difficult to do when the degradation is high. For example, when temperatures are high somewhere in Spain, I think that the degradation is usually higher.
Cool, that's really interesting, and reveals my ignorance as well. I used to watch Formula One many years ago when refueling was an issue. So, any more questions and comments? Okay, well, just in response to one of Julio's points, assuming you don't have yet a working paper version ready, I will endeavour to put the YouTube of this talk, or the video of this to you on YouTube as quickly as possible, assuming that you're happy with that, Daniil, and then others can look back over the recording and potentially give you more comments in due course.
Yeah, okay.
Great. Okay, I'll do that. So it should be up. I'll try and get it up today or on Monday. Thank you very much, Daniil. That was a really interesting talk. Thanks also to your co-authors, Dimitri and Gleb. Good to see you all, and look forward to seeing some of you in person later on this year. And I wish you all the best. Thank you very much, everyone, for your questions, comments. Thank you, Daniil, for a really interesting presentation. And we are going to meet again next week. Next week, our talk returns to football. I think. I don't actually. I should check. I'm fairly sure it is. But the talk is by Vincenzo Alfano on From Colonial Empires to Umpires, an investigation into the rules, into the role of colonial legacy in attitudes towards subordinates. So, wish you a happy weekend, enjoying the various sporting events that are on at the moment, and I look forward to seeing you all again next week. Thanks, everyone.